So, talking about relativity and talking about this problem with the muon that's being formed at a particular distance above the atmosphere. Okay, so muons are leptons that are being. I think it's a lepton. Yeah, I'm pretty sure it's a lepton. That's being formed in the high atmosphere of the Earth. They have incredibly short life expectancy. They only manage to survive a few microseconds. I think it's a microsecond before they disappear. But interestingly enough, they have relativistic velocities. I think they travel at 0.98 c. They travel incredibly fast. So they're traveling at relativistic velocities. Well, the muon, even though they travel at relativistic velocities, without the idea of relativity, the incredibly high velocity that they do have would not allow them to reach the surface of the Earth, okay, without the idea of length contraction or time dilation. So a muon that's being formed at high altitudes at the Earth, at approximately 20 kilometers above the surface of the Earth, 20 kilometers, would not have enough time to reach the surface of the Earth, okay? But in a relativistic universe like our universe, which we are in, it turns out that the muon doesn't see the distance from where it's formed to the surface of the Earth as 20 kilometers. It sees it as a much shorter distance than that. And because of that, the muon will actually have an opportunity to reach the surface of the Earth. It turns out, without the idea of relativity, that the possibility of a muon living long enough to start from high atmosphere to reach the surface of the Earth is maybe 1 part per billion. Okay, not a very good probability at all. As a matter of fact, I wouldn't put a lot of money on that kind of probability. I think even the lottery has a better chance of winning than, lottery. You have a better chance of winning the lottery than a muon to reach the surface of the Earth. The truth of the matter is that almost every single muon that is formed in the high atmosphere of the Earth does reach the surface of the Earth. And the reason that happens is because of relativity, and not even special relativity, not even general relativity, but special relativity. So what this problem entails is proving that it is possible for muons to be created at high atmosphere and reach the surface of the Earth. So let's talk about that. First need to start off with our length contraction equation. We have the length that the muon sees, okay, from the point of view of the contracted length, if you will, is equal to the proper length, which is the length in which we see in a stationary reference frame. Now, mind you, it's all relative. Our reference frame is not necessarily stationary, but we're going to take it to be stationary, divided by my Galilean transform, okay, or my Lorentz transform. Okay? That translates into the equation of proper length times the square root of 1 minus the velocity of the particle squared divided by the speed of light squared. Okay? So that is going to give me my visible length. Okay? Now I'm saying that the muon is traveling at approximately 98% or percent the speed of light, which is incredibly fast if you think about it. Okay, so what I'm going to do is I'm going to put in the proper length, which is 20 kilometers. Okay, I'm going to multiply that by 1 minus 0.98 squared divided by 1 squared. Okay? And that is going to give me the length in which the muon can see. Okay? That will give me the length that the muon sees here. It'll give me what's called the contracted length. Okay? It turns out that contracted length is approximately 2 kilometers. Okay? So that means that the muon is seeing I should say approximation, that the muon is seeing only a tenth of the total distance. It sees this as only being 2 kilometers. It sees the surface of the Earth here and not way down here at the 20-kilometer distance. Okay? So it sees the distance from where it's being formed to the surface of the Earth as being only a 2-kilometer distance, where from our point of view, it's a 20-kilometer distance. Okay? Cool? That's what the muon is going to see. Now, if you can go ahead and do the math, 1 minus 0.98 squared divided by 1 squared, that's the advantage of using velocities as a percentage of the speed of light. Instead of converting this into 3 times 10 to the 8, and this to be 0.98 times 3 times 10 to the 8 squared, it just simplifies things. Now, if you think of it as units, the units drop off anyway. Keeping this point here, I don't really need to keep a hold of those units as meters per second, because the only unit that's going to buy is the unit out here. So we're talking about kilometers. My answer in kilometers, and I should say kilometers. Okay, or whether I'm talking about light seconds or light minutes or light years, those are all distances. They're going to give me a result in that distance. Okay, so that gives me the length, the contracted length. Now the next step is asking you to solve how far does the muon travel. Okay, well that's a simple problem. The length that a muon travels in its lifetime is simply going to be its velocity times its time. Okay, so I have the information of how long that piece of light is going to survive. I have the information of how fast it's going to travel. Now that is going to be this 0.98 times 3 times 10 to the 8 meters per second, because I want it to be expressed in meters per second, because the time is going to be, remember, 6 times 10 to the negative 6 seconds, if I remember right. It's terribly, terribly short. I could be wrong on that time. Once I multiply that through, I'm going to get the distance that the muon is going to be able to. It's not relativistic. It's not relativistic at all. I don't have to treat it as relativistic. I can make this problem a lot more complicated than it actually is by solving for a time dilation over here. But I don't need to. I don't need to for the purpose of this problem. I don't need to use a time-dilated time. If the muon only believes that it's going to exist 6 times 10 to the negative 6 seconds, then I'm just going to take its expected life expectancy from its point of view, its velocity from its point of view, and to get the distance that it's going to travel in its point of view. Now I can compare that distance to that distance to determine whether the muon is ever going to reach the surface of the Earth from its point of view. It turns out that these lengths are about the same, and they turn out to be approximately 2. So that from its point of view, believes that it'll reach the surface of the Earth. Well, it does. It turns out almost every single muon formed in the high atmosphere reaches the surface of the Earth. Okay? And that's proof of it. Cool? Now, other things that are being suggested is, if this is the muon's projected distance at its point of view, that the muon sees it contract, it only travels a distance of this, all of this remaining distance left to travel. Okay? So from our point of view, the muon shouldn't reach the surface of these. Okay? Cool? The problem with that assumption is not taking the relativistic point of view. If I were to watch the clock for the muon, I can determine that its time, its clock, in which its life is slowly ticking away on, is going to be much, 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 much slower, allowing the muon to travel around some distance. Or I can use the length contraction idea where the muon only sees this distance to be only 2 kilometers. Okay? So from a non-relativistic point of view, that particle is out 20 kilometers. But in a relativistic point of view, whether I'm using length contraction or time dilation, that particle will reach the entire length. Okay? So to solve for that length contraction, I'm going to get this. To solve for the expected distance that it's going to travel, I'm going to use classical kinematics to solve for that. Okay? So that should give you the solutions to all 4 parts of this problem in my problem set. Okay? Oh, I should rewrite that so you guys can read.